Here we're going to talk about how we're going to draw Lewis dot structures, and we'll have a few examples at the very end. So here are the rules for drawing Lewis structures. You can certainly pause and read through this, but in general we're going to arrange these atoms that you have that you're trying to draw a Lewis dot structure for. The least electronegative should be in the center. Hydrogen should always be terminal. Then you should connect everything with a single bond. After that, calculate the number of valence electrons on all of your atoms combined. If there is a charge associated with it, you need to change the number of valence electrons you're referring to. So if it has a -1 charge, add an extra electron, for example. Then we're going to subtract 2 electrons from each of your single bonds that you've drawn already when you've connected everything together. You're going to have some amount of remaining electrons left over to fill in. First and foremost, fill lone pairs on the most electronegative atoms first. If you did everything right, those should be the terminal outermost atoms. And again, that will exclude hydrogen. Hydrogen doesn't need 8 electrons, it only needs 2. And you're filling these in as lone pairs. Don't create double bonds yet. You need to wait until the very end before you start making double or triple bonds. If you have any electrons left over after you've filled the octets of all of these outermost atoms, then place all of the remaining electrons on the central atom as lone pairs. Again, not as double bonds or triple bonds just yet. Only once you've used every single electron, every single valence electron that you've counted, only then should you start creating double bonds or triple bonds. And you'll do that to try and satisfy the octet of the central atom. And that's if the central atom would like an octet. Remember, one exception to this was group 3A. Well, group 3A actually doesn't need an octet. It can have just 6 valence electrons, and that's okay. But we will talk about that later. But generally, these are the rules for going about forming a Lewis dot structure. This matters because this can give us some indication of the chemical bonding. So if there's a double bond, that means something different than if it's a single bond. We talked about bond distances being different and bond strengths being different. And in the future, this will also give us an indication of the geometry of the molecule. So that's why we like drawing these Lewis dot structures, and it's a central feature for general chemistry. So we really need to become quite proficient at this. So let's try and draw a Lewis dot structure for carbon disulfide. So often also the central atom is going to be the thing that's alone. So here we have carbon in the center. It's the least electronegative, and we have sulfurs on the outside. A lot of times if you have multiple atoms that are the same, those will often be on the outside anyway. If there is a difference, if this rule does not work out in a particular scenario, I would have to give you which one is the centralmost atom. And there are a few examples like this. Okay, so I have sulfur, carbon, and sulfur, and I'm going to connect everything with at least one bond line here. And I'm going to count out the number of valence electrons. There's no charge on carbon disulfide, so I just need the valence electrons. There's 4 valence electrons for carbon, and there are 6 for sulfur. So going to be 12 total there, right? Okay, so we should have 16 electrons that we are dealing with, 16 valence electrons. I've already used 4, right? So since I've used 4 because each single bond is 2 electrons. I've used 2 single bonds, so I should have 12 electrons left over. So now I start filling in the octets of my outermost atoms, starting with the most electronegative atom. So we only have 2 sulfurs here, so it doesn't matter which one, but I will fill in the octets as lone pairs for the outermost atoms. Here I've used all 12, right? I use 6 on this sulfur, 6 on the other sulfur. So that ends up being all of the electrons. If I had any extra electrons left over at this point, Okay, so 12's gone. If I had any electrons left over at this point, I would start adding lone pairs to that central carbon. Not double bonds yet or anything like that. Once I'm out of electrons, which I am now, now I convert to trying to make sure everything has a satisfied octet. If I did everything correctly, my outermost atoms should have a satisfied octet, which they do. Right, sulfur has 6 in terms of lone pairs, and then a bond, which is also 2. This is a covalent bond, so sulfurs are good to go. So what I'll do is carbon only has 4 valence electrons currently. One from one of the bond, or two electrons from one bond, 2 electrons from the other bond. So now I will start converting lone pairs into double bonds. I can't change the number of electrons. I can't just start adding double bonds or adding lone pairs to the carbon because I don't have any more electrons left over. So what I'm going to do is I'm going to actually take these electrons from the lone pair and put them in a double bond. And I'm going to do one from each side in order to get a filled octet for the central carbon. So I'll have carbon double bond to sulfur. Sulfur now, since I converted one of those lone pairs, this one will now only have 2 lone pairs on it. It still has a filled octet because of these bonds that are being shared. So it means that this should be my final valid Lewis dot structure for carbon disulfide. You can see carbon has a filled octet currently. It has 8 valence electrons, 2 from each of those bonds. And there are 2 double bonds, okay, so 8 total electrons. And the sulfurs still have their valid octet. So this matters because what we now know about carbon disulfide is that it has 2 double bonds associated with those carbon-sulfur bonds, which are stronger bonds and slightly shorter bonds than what you might expect with a carbon-sulfur bond. Let's try another few of these. Here we have carbon tetrachloride. Same thing, we're going to start with carbon in the center. We have 4 chlorides coming off the center, and I'll just add those right away. We have Cl, 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 Cl. Okay. I need to count up my valence electrons. So chlorine has 7 valence electrons, and carbon has 4. So here we should get 32 valence electrons total. And now remember, I've already used electrons to form these single bonds. I've had 4 bonds, so there should be 8 electrons that I've already used here, right? Okay, so I should have 24 more electrons that I can use. I think you can see now I'm going to start filling the octet of the outermost outermost atoms, which are the most electronegative. And I think you can see 24, if I put 6 more on each of these chlorines to fill the octets of each chlorine, I will end up having diminishing all of the electrons. So I've used now all 24 electrons. Again, if I had more electrons, you would start adding them to the central atom. If possible, here carbon already has a filled octet, so we wouldn't have been able to do that anyway. But this would be the valid Lewis structure for carbon tetrachloride. Again, we're seeing some characteristics. Carbon has 4 bonds to it total, and they're all single bonds, carbon to chlorine. So, and again, this will give us some more information in the future. So let's try ammonia. Again, hydrogen is always terminal. Nitrogen's the, that means nitrogen must be in the center here. So we have nitrogen to hydrogen, hydrogen, hydrogen. It doesn't really matter how the geometry in which you're drawing these, where these hydrogens are located, because we're not really dealing with geometry just yet. In the future, we'll care a little bit more about this potentially. Now we'll count up the valence electrons. We have 5 from nitrogen, and each hydrogen has 1, and there's 3 hydrogens. Okay, so there's 3 hydrogens, each of those have 1 electron. Okay, so we should have 8 total. we've already used 6 to connect everything together. Okay, so now we have 2 left over. We do not have to fill the octets of the hydrogen. Hydrogen does not need an octet. It only needs a duet. So they are already done. Hydrogens won't have lone pairs on them. So these 2 electrons, since we have leftovers, will go on the central atom. So my 2 final electrons will go on that nitrogen. And I think you can see here, nitrogen has now a filled octet. It has 2 from this hydrogen, 2 from this hydrogen, 2 from that hydrogen, and then 1 lone pair, which is 2 total electrons. So there are 8 electrons associated with that nitrogen. So it has a filled octet. So what this means for us is that nitrogen has a lone pair on it in ammonia. That might not be readily obvious by looking at NH3, but that's something that we can determine with that Lewis dot structure. You'll definitely want to try a bunch more of these on your own, and this will start getting more complex as we get polyatomic ions once they have charges associated with them. And sometimes it won't be as readily apparent where you will form a double bond or a triple bond or something like that, and that will get us to future ideas like resonance structures. So that's a future topic.